Now we will have Lukas Eisert, Inferring the assembly and merger histories of galaxies with the IllustrisTNG simulation and machine learning. And you start whenever you're ready.
Yeah, sorry that.
Ah, perfect. Okay. And this. Ooh. Okay. So hi. First, I have to say that I had a bad cold last week, so I still have to cough all the time. So sorry for that. So as said, my name is Lukas Eisert. I'm coming from the Max Planck Institute for Astronomy from Heidelberg, and I will shortly tell you about my current PhD project, Inferring the assembly and merger history of galaxies with IllustrisTNG simulations and machine learning. So the basic idea is quite simple. So here on the left side we have two galaxies. They merge or interact to the galaxy on the right side, and basically the problem I'm dealing with is that we can only observe that one, only the last state of each galaxy in its evolutionary history. And the question I'm asking is, what can this observation tell us about the simple history of that galaxy? And if I'm talking about observation, what do I mean? So first, of course, we can look at the galaxy itself, so the main body, and at its morphology and its properties. So for example, if you look at the diskiness, if you have a massive merger, we would guess that this massive merger could disrupt the disk shape of the galaxy. So that would tell us something about the merger history. We have such informations in large quantities, for example, from SDSS. Another thing I want to look at is the stellar halo, so the stuff around that main galaxy body. It, as the name says, consists out of stars, and from simulations like Illustris, we know that these coming mostly from accreted galaxies. And we also know, to some certain extent, that these features you see here, so the shells and the streams, are also related to the merger history. So there's a good idea that this will tell us a lot about the merger history itself. The only big problem is that these things are quite faint and hard to observe, because we are talking about surface brightnesses down to 32 magnitude per arcsecond squared. But in general, we have now this information in the observations. Now, the only problem again is we only have for each galaxy one observation at the last time. So what can we do? What I'm now doing is that I go to full cosmological simulations, so a full box full of interacting galaxies. For each galaxy, I can then get the last state, the observations, and the whole story of that galaxy. So what I'm doing is basically a simulation-based interference. Now, the simulation I'm using is IllustrisTNG. So that's such a type of a full cosmological simulation. And in my case, especially use TNG 100 as compromise between the resolution and the sample size. So in the end, I end up now with 150,000 training galaxies and 80,000 test galaxies I can use my models on. So that the overall setup of my whole project or PhD looks not like that. So on the left side, we have the physical processes which are not observable in general. In my case now, the merger statistics, and I use up to now 4 statistics. Summary statistics, that's the average average mass ratios, the average lookback times, and also the time of the last major merger, with the idea, of course, that the last major merger have the biggest impact on the merger history. And also the fraction of exsitu stars, so the stars which have been accreted during its history. And I'm using now the simulation, IllustrisTNG, to connect this to the observables on this side. And now I want to use machine learning to go the other way around. And I'm doing this basically in 2 steps. Approach number 1 is do the feature selection myself. So I think about which observables could be most interesting for the merger history. In my case, I choose those. So the stellar mass, the redshift, the diskiness, the galaxy size, the average stellar ages, the color of the galaxies, and metallicity. And the other thing is, of course, that we can say that I want to do deep learning, so the model should figure it out itself. So I'm only doing mock observations from the simulation and fit it directly. I'm doing both, in fact, at the moment. In this talk and in the first paper, I will first not only go over the features I selected myself. The big twist is now that I'm not only doing point-to-point prediction here, but I have to look at that this is, of course, an inverse problem. So that the way from the non-observables to the observables is connected to a certain loss of information, of course. So I won't get one merge history to a certain set of observables, but it will get a posterior distribution. So a probability that a certain merge history is compatible with a certain set of observations. And the model I'm using to do so are conditional invertible neural networks. So they are also from Heidelberg here. So there's also the repository with the framework. You can build this yourself. And it's quite easy because it's just an invertible neural network, as it says, between the space of unobservables and the Latin space set, and this is conditioned by the observable C. So, and all you have to do if you want to train this, so I put in now my 150,000 training galaxies, the observables from the simulation, the unobservables from the TNG simulations, and I train this with the maximum likelihood loss, such that in the end, these data points here are transformed into a Gaussian in the Latin space. And then I can use this together with the invertibility of that network that I can basically sample back. So I have this Gaussian on this side, and I'm sampling given a certain observable, which goes again inside here, and I get points in my space X, and then I can simply do a kernel density estimation and get my posterior in that space. So what I basically have is something like a generative model where I map the distribution of merge histories into a Gaussian on this side, conditioned by the observable C. Another important thing maybe to mention is that this architecture consists of non-invertible sub-networks. So at the moment I'm using multiplayer perceptrons, but you could also use convolutional neural networks to make this work for images, for example. So I'm doing this now for my 18,000 test galaxies. First, I want to show you the results for 9 randomly chosen of those galaxies. So in each row, each of the example galaxies of my test sample, and each column, one of my statistics I'm inferring. So the mean merger lookback time, the mean merger mass ratio, the lookback time of the last major merger, and the fraction of exsitu stars. And in each panel, I'm showing you the prior in gray, so the overall distribution of that parameter over the whole sample. I show you in blue the curve, which is given by my model. And to compare this with the ground truth, I show you the ground truth as red line. And you can see in most cases that the blue curve, the posterior, is following the ground truth very well. Of course, it's a limited statement for 9 example galaxies because, of course, for example, in this case, you see that the ground truth lies quite outside because it can't always be at the peak, of course. We see, very important for the mean merger mass ratio, you see that the posterior is always close to the prior. So that's a bad thing, of course. That's the way the model tells us that the observables I'm putting in are not much informative for that parameter. But of course, it's a good thing because the model tells us this. And another thing is the lookback time of last major merger. You see there's an additional bin because there are galaxies with no major merger. And what I did here was something like a combination of a recursion and a classification. So I have an additional bin for the ones with no major merger. Now I want to also show you this for all 18,000 test galaxies. To do so, I am summarizing the posterior just with one estimate, so the maximum a posterior estimate, so just the peak of the blue curve, and compare this to the ground truth. So I'm plotting now the orange lines against the red lines for all of these. For all 18,000 test galaxies, what I end up is this. So on the y-axis, the map estimates, and then the x-axis, the ground truth for each of the parameters. And again, we see for the mean merger mass ratio, the peaks of the maps are always close to the prior peaks. So that's really a hint that there's not enough information. We also see here, of course, the lookbacktime of last major merger. In general, you see the ones which had major merger and are predicted to have so fit to a certain extent, but in general, this is too complex to look at this via the map. But we see in general for the exsitu fraction, also the mean merge lookback time, that this works quite well to this point. Now, this is only the map, and now I can go back to the posteriors, what I did now, example for the exsitu stars, and look if that error, so the error here, around the best case, the diagonal, is related to the standard deviation of the posterior. So I've plotted the posterior standard deviation against absolute map error. Oh, where's this going? So here, there. And you see that for small posterior standard deviation, there's also a small map error. And for large posterior standard deviation, there's a large map error. So in general, we can see that from the posterior, this is indeed, we can interpret it as an error bar for that prediction. And it's already quite cool because we have now just this very small set of hand-selected features, and we already get quite well prediction with error bars. And I mean, most of the points lie well within plus minus 10%, so we are well able to distinguish low from high exsitu galaxies. And that's also now the main result of of this project, of the first part of the paper, which will be released this year. What in the full paper, there's also further conversion analysis, of course. I will have a closer look at these other two things, or the mass ratios, to really to really see that this is not a problem for the model, but the problem of the observables. I will have a closer look at the lookback time of the latest major merger, of course. And most important, I will do a sensitive analysis, so to have a look which observables are most important for the histories. So and this can then also used as justification, because I see that the morphology, like the diskiness or the galaxy size, is very important for the prediction. So that the approach 2 is justified, and there I'm also working on at the moment. So I'm mostly working on at the time to get representation via contrastive learning from these nice images here on this side. This is now from TG50. But I'm also working on, with of course, basic idea then bringing this into the conditional inferable neural network again. And another idea is then that I'm also letting the model itself choose the correct merger histories, so that I don't have to do this selection of summary statistics in the merger space. And the overall target, of course, in the end is then to apply this to real observations. So. Thank you.
Thank you. So, did you replace thereby semi-analytic galaxy models? Not yet. Not yet. Questions? So you get individual merger trees for, well, not yet, but potentially for observed galaxies, right?
Yeah, what do you mean? That's the overall target then.
Yes, yes. Yeah. And
but not yet.
Do you have an idea how much variability over the merger history of a galaxy you will see when you do this exercise?
No.
Probably you reconstruct the more recent past more accurately, and then it gets fuzzy, or?
You mean then from observations? Mm-hmm. Yes, I guess so. I mean that's the reason why I also looked at the latest major merger. I mean these statistics I'm using are mostly also influenced by the recent history.
Mm-hmm. So. How far back do you think the history is relatively unique, and then it becomes bimodal or trimodal?
That's a hard thing to discuss yet, I must say.
Yeah, I'm just asking for a guess.
Yeah, okay. Because it's difficult.
Do we have something on Slack? Okay. From Helena Dominguez Sanchez. Did you check if there's a correlation on badly recovered parameters for the galaxies, i.e., there are galaxies for which all the estimated parameters are wrong?
Sorry, I didn't understand. Yeah, thank you. Wait, the low one.
The lowest.
On badly recovered parameters. Yeah. I in fact did this. So basically, I looked for which type of galaxies, the prediction are worse, and indeed, it's the galaxies mostly then without disk. So elliptical galaxies were red. So that's the case where the prediction becomes more ambiguous.
Mm-hmm.
Yeah. I can then also write more details on Slack.
Another one. A longer one.
First question.
So the mic. Sorry. Gosh. I'm sorry. So which one?
The first question, yeah.
That's the question.
Okay, yeah. Great talk, love the start. Could you comment a little bit on CINN? Why do you choose them versus other options? Your experience using them? From Mike Wormsley.
First, they worked. That's, of course, the main reason. And they are really easy in the general. That is easy how they are built up, and they're easy how you train them. They're easy how you use them. So I really love them because they're easy and powerful. And especially if I compare this to other architectures I saw.
Okay.
So that's really something I can recommend to look at.
Thank you again. And